Thank you, Fred, for a kind introduction. I think some of it was true. I rant a lot. Okay, so I've been given strict instructions that I speak for 40 minutes, so you'll just have to stop me and don't be shy. Many years ago, someone said, there's no limit. And that was at 2 o'clock. And at 8 o'clock, people really wanted to go to dinner. So let's not repeat that. Okay, so I'll give you a sort of a snapshot of what machine learning force fields are, what they can do, and where we are with that today. And then and leave a lot of time for questions. I think it's a diverse audience, so I hope that there will be something for everyone, depending on your background. So to set the scene, I always brought out this multi-scale modeling slide because it gives you a sense of timescales, length scales, accuracies, gives you a picture of what can be done with different methods. So I have both time and length scale on the horizontal axis. So lengths in terms of number of atoms and timescales, and the techniques that we have on the far left here are exact. And to the extent that quantum chemistry is not exact, that's the department of philosophy, right? So in practical science, we know very well where the known equations of quantum chemistry fail, and we are so protected by many, many orders of magnitude in length scale and energy from those failures. But of course, it's very, very expensive. So if you want to go up and simulate more than a couple of atoms or any time scale whatsoever, then you need approximations. And this was known by the people who invented quantum mechanics, knew this. Paul Dirac famously said that now that the Dirac equation is known, the rest of chemistry, physics, and biology follow. It's just that the equations are hard to solve and approximations need to be developed. So you can think of this as the Dirac program that we are in and have been for 100 years. And of course, then the vertical axis is error. And I put boldly 0 here for quantum chemistry. That's the world we live in. But these errors go up quite quickly as you move through these different methods. And here, KT is my unit. So that's room temperature, things that happen in the lab. And I want to predict the rates of those things, then I need accuracies of processes on the order of KT. Now, all of this science that I'm doing fits into this broader broader approach of first principles modeling. That is a very odd thing to do for a natural scientist. I spent the last 20 years in engineering, in an engineering department, and not a single person in that department really knows that this exists, because it's very weird. Normally, a natural scientist goes out into the world, or an engineering scientist goes out into the world, you see objects at some length scale, on some time scale, and you want to understand how they interact. And that's what you do. You don't say, I know everything on the atomic scale. What follows for the properties of a bridge across your river here? Right? That's not a useful thing. When things get very small, where it becomes very, very hard to observe the objects and what they do, it actually is the only thing you can. It's a very, very, very useful thing. And that's what quantum chemistry and these techniques that are derived from quantum chemistry do. So I assume the equations and I calculate, approximate, systematically derive what happens. And if you look at the literature, if you Google this word, first principles modeling, this phrase, you find that it has sort of taken on the synonym of electronic structure theory, because this is where you talk about electrons and how they behave in the field of, once you fix the ions somewhere, the nuclei, and you ask how the electrons behave, that is when you can do. If you want to do millions of atoms, you do something called force fields, so empirical force fields in particular, which is a model like every other natural science model. It's not bottom-up. You assume some simple interaction between the atoms, you fit them to some data, you cross your fingers and hope. And some of that data that you fit to may come from a lower level calculation, but then ultimately it comes from the laboratory, and you use spectroscopy and solvation free energy and thermodynamics to fix the few parameters that you need. But of course, the problem is that these models then are not transferable and have severe limitations. So what the program of machine learning force fields is to forget that top-down modeling and really try to push the idea of first principles modeling further up, get rid of the electrons and arrive at force fields, simulate microseconds and millions of atoms. And we need machine learning to do that. So 20 years ago, we didn't have the computer power, the understanding of how to handle models with millions and millions of interacting parameters. But now, understanding is a big word, but now we certainly do that. And so we can do molecular dynamics with a speed up of, let's say, 1 millionfold, depending on the system size, with essentially no loss of accuracy for the observables that molecular dynamics gives you. So that's the program that I've had to start in the last 20 years, and that's what I still do, and that's what I'm going to tell you about. So density functional theory is along the way there, and it is worth noting that it has been a huge success. So electronic structure, bottom-up modeling of materials has been immensely successful. So let me throw up a few things that people regularly compute with density functional theory. So phase diagrams is the most basic question you can ask about a material. Is it a liquid, a solid, a gas? What kind of solid it is the phase diagram. And you can push that to extremes in temperature and pressure, many, many thousands of Kelvin, 10,000 Kelvin here, and many, many thousands of gigapascals. The Earth's core is at 500 gigapascals, right? So this is way beyond anything we can create on Earth in the laboratory. And you can ask, what is carbon look like? Going on a much smaller, sort of less extreme case is solutions. So solution chemistry is something that is a lot of life, a lot of the chemistry that you want to do, even if you want to end up with something that's dry, often the process alongside is wet. So thinking about solutions is very important and understanding them. But atoms are small, timescales are very short, and explicit experimentation on how ions get solvated, all these different polyatomic ions, you're not going to get from just from experiment. So we can do calculation. The little inset here shows you that a roughly X equals Y line of ionization potential. So that's something that you can measure experimentally and calculate. What's the energy of removing one of the electrons? And once you see that that is basically correct as a function of the ion and the solvent, you believe your model, and you can then go and investigate the structure and dynamics of all these ions. The surface science is another area where density functional theory, bottom-up, first principles, electronic structure theory has really gone hand in hand with ever better microscopy. So this is a titanium oxide surface where a molecule is attached to titanium oxide. And this is an experimental image, but you don't quite see the atoms. You don't see the molecules. You can't follow the atom by atom, bond by bond evolution of the change that these molecules go through once they attach to this very active, this catalytic surface. But if you turn on density functional theory, you can follow all the reactions and all the atoms. And lastly, I just pulled up an image of a forest of carbon nanotubes. This is nanoscience, carbon-based nanoscience, and which has been really on a roll for the last 20 years, maybe 25. And in understanding how nanostructures form from carbon has really been only possible because of density functional theory. In general, zooming out a little bit, we can get material properties, stability, thermal and dynamical properties, catalytic reactions depending on the surface and the molecule. There's a whole other area of drug properties. So the drug discovery as a human enterprise uses bottom-up computational modeling to tell you about proposed drugs and help them filter help filter them down into to things on which it's worth experimenting on. Semiconductor industry as a whole for the past 40 years has been a huge user of electronic structure theory and calculation to investigate defects and interfaces. But this is very, very expensive. So computing things really with the electrons in there costs a lot of compute. So a low-level density functional theory calculation with about 100 atoms, and on one compute node, let's say you have 100 cores, it takes you 1 hour. And that's the single energy of a structure of where you've specified where the atoms are. And it's cubically scaling in this regime. So if you double the number of atoms, it's going to be 8 times more costly. For 1,000 atoms, it will be 1,000 hours. For a slightly better level of DFT, DFT has different levels of accuracy depending on what you can afford and what you need for that particular observable. You can easily pick up prefactors at minimum 20, sometimes 50, and the scaling of n to the 4. So 1,000 atoms would cost you 200,000 hours. And if you want to go better than DFT, the DFT is already an approximation of quantum chemistry, but this sort of gold standard coupled cluster theory with singles and doubles and triple excitation, let's not go into the technical details, but it is a set of controlled approximations. It scales as n to the 7 in typical implementations in general. And no one has done a calculation on 1,000 atoms, and likely no one will, because it takes 10 million hours and you only get one energy. So it's probably not worth it. You don't learn very much from a single energy. And so normal DFT is the workhorse. And this is a few years old now, but it's the histogram of the UK's largest academic computer. And you can see it's ordered by the kind of usage of the different codes. And VASP is one of the most widely used DFT codes. And it takes about 35% of all compute. And if you add up all the other DFT codes that are labeled green here, so this part of the diagram, together they add up to about 40%. So 40% of non-military, non-meteorology, and non-commercial academic compute basically is doing density functional theory, and most of it is doing molecular dynamics. So what is that? You take the atomic positions, you compute quantum chemistry in the approximation that you like, typically DFT, and then you get forces on the nuclei, right? Which way do the atoms want to move? And then you plug that into Newton's law. So that's it. And then you just go and iterate, right? And each time you solve the equations, the quantum mechanical equations to get your forces, and you go back. And the rest of it you throw away, more or less. The wave functions, the electron density, you can use them to reinitialize the next step, and that's why it's worth doing at all. But more or less, you compute all this information, but you retain very little of it. So the idea of force fields is to just not do that and go from atomic positions to the forces directly. Make that mapping in a direct analytical manner. Right? It's a map. If you have n atoms, you have a 3 to the n dimensional system of coordinates, right? X, Y, and Z for each atom. So you have an R to the 3n space, and you're looking to map that into the set of real numbers, the energy. And then once you have that, you can take, especially if it's analytic, you can take gradients, and that will be fine. And of course, this is not a new idea that you want to make these direct mappings of the real potential energy. And quantum chemists have been doing it for many, many decades for very, very small systems. So a water molecule, 2 water molecules, maybe 1 ion and 2 water molecules, and so on. But all those methods that do this in a very controlled and precise manner scale exponentially with the number of degrees of freedom. Typically, they're based on polynomial tensor networks. And so the question is, can we do this in general, not just for small molecules, but materials, large molecules, and molecular assemblies? And the kind of things we want to do, here's a very funny molecule for which no one, even though it's small, its electronic structure is very, very complex. So no one has done anything like this. And this is a very complex system. It's actually, I call it a baby battery, right? So it's got a bit of copper, an anode, lithium, an electrolyte, cathode, and you want to just run it and see what happens. So how do we do this? We use machine learning, which means taking some data, so data at the level of, let's say, density functional theory or any other, sometimes higher, more accurate levels of theory, but at a size where we can afford it. Remember the steep scaling, n to the 3, n to the 4, n to the 7. So we can't make these too big. But you take configurations of atoms, and how we generate them is a kind of a whole other detail, but very important detail. But once you generate a number of structures, they become points on this high-dimensional potential energy surface, and you want an interpolant. You want to essentially take these data points and come up with an analytic function that goes very close to them. And for this, you need to represent the atomic environment somehow, parameterize them, and then do regression. And regression can be linear regression, kernel regression, neural network regression. Different people do different things. And then you want to predict the energy. It turns out that it's good to predict the energy of each atom, because then it's linear scaling automatically. If I have a twice as big a system, I just need to predict the energy of each atom, and F would be the force. And if it's not good enough, you go back and get more data. So when this idea was proposed, and 20 to 30 years ago, all the quantum chemists said, this sounds great, it'll never work, because you need to go back so many times. How much data do you need to do this in a level that is useful? And that matters, right? It's nice, we're talking about physics and chemistry, but actually it's a bit like engineering, right? If I made an interpolant like this, but it cost me 1 billion input data points for it to be sensible and useful, no one would ever use that method, because by the time you've generated the data, you've probably solved your problem. Okay, so this is sort of engineering in that cost matters. And again, the whole enterprise is completely worthless if the cost is too high. And everyone thought, based on the exponential scaling of the early methods, and just generally our inability to comprehend high-dimensional spaces, so people thought, well, atoms can be anywhere. The space is too complicated, too complex. And so it will take you as many data points, as many atomic configurations I can imagine, and that's a lot, and so it's not going to work. I'm standing here talking to you, as you can imagine, not a spoiler, that it did work. That was not assured. This is an empirical question. This was the first time when I saw it happen. It's a paper from 2014. It's on tungsten, and we did something very, very simple. Take bulk tungsten, BCC metal, and add some defects to it, some vacancies, open some surfaces, so different orientations, and try to make a model that reproduced the density functional energy. And previous attempts at modeling are these green and blue points analytically, not with machine learning, but with very few parameters. And it turns out that this is hard. So what I'm showing you here are DFT reference energy errors, and these are percentage errors of these various properties. So the energy of a vacancy, taking out an atom from the crystal, opening up a surface, these are elastic constants. So how much energy does it cost to shear or dilate or stretch the crystal? And all these different models span 3 decades of development, and they're kind of useless quantitatively. And the first time we turned on a machine learning approach with this sort of idea, and we collected 200,000 atomic environments, they were assembled in 6,000 configurations like this one, then you just nail it. Okay? Everything comes out like the precision that exceeds on what you need to. So now let me take a few minutes as an interlude, and ask a mathematical question. What would be good descriptors of local environments? All of these methods, all of the force fields predict the energy of an atom by asking, where are your neighbors? Right? That's what we're going to do. So what would be a good set of descriptors for asking where your neighbors are? How do you describe a local environment? You want symmetries. So you want this neighborhood descriptor to not depend on whether the atom has these neighbors or these neighbors, right? If I rotate the laboratory frame, the energy doesn't change. It's a symmetry of the world, so I don't want my descriptor to change. If I translate the atom, my atom is over here in this environment, I translate that atom, I have this same environment, the energy shouldn't change. And permutation symmetry is that I don't care which of my neighbors come in what order in my list of neighbors, right? That we know, again, from quantum mechanics that atoms are interchangeable, so the energy shouldn't change. And then there are a few other things. I want uniqueness. So if I have two different molecules that have the same descriptor, or two different environments that have the same descriptor, they're going to have the same energy in my model. So I better have a mapping that if I have that there shouldn't be two environments that are different but mapped to the same descriptor, because then I'm going to get the same energy for two different atomic environments. Reality is not going to give me the same energy, so that's an inherent, it would introduce a limitation that you can't break. And then lastly, the potential energy is smooth and continuous. So we know that from quantum mechanics, that as you move the atoms around, you can test that numerically. The energy is a very, very smooth function. And of course, I want something, that's the deal in machine learning, that I want something that's systematically improvable. I want to be able to refine my description if I want more accuracy. So it turns out that satisfying all of these criteria, coming up with a set of features, is an unsolved mathematical problem and was not very well developed 20 years ago. So let me just illustrate why this is, why it looks interesting and why it's actually a difficult problem. So let's back up a bit and I'll give you 6 sticks. So here are the lengths, and I ask what sort of tetrahedra can you assemble from these sticks? So here's one, and when I give this talk in Cambridge, I hand out a physical model of this particular one. But of course, I can take the same sticks and let's analyze it. It has these triangles in it. And it turns out that I can assemble a different tetrahedron from the same 6 sticks that don't have these triangles, which means that this tetrahedron and this one are not the same. They're not permutable or rotatable into one another. So what we learn from this is that specifying the 6 sides of a tetrahedron is not enough in some unordered manner, so that I have permutation events, is not enough to specify the tetrahedron. So this may surprise you. The question is, what is enough in general? I'm just talking about 4 vertices here. I want to answer this kind of question in its generality. I have endpoints in space. What do I need to specify in order to have a permutationally symmetric but unique description of that environment? So the fact that distances are not enough is actually known in the literature. So this is an example now more focused on atoms. So here's my central atom, and here are my neighbors. And imagine that I have 1, 2, and 3, and then either I have my 4th neighbor here or my 4th neighbor here, 4 and 4 prime. And so this is the textbook example where what I've listed, the fact that these are, obviously they're not the same configuration, 1, 2, 3, 4, and 1, 2, 3, 4 prime. And the angles between the particles is listed here in this pairwise diagram. And we can see what happens, so that the top is 1, 2, 3, 4, the bottom is 1, 2, 3, 4 prime, and all the angles between the blue atoms are the same, and then the red atom that I'm moving, 2 angles, alpha and pi minus alpha, swap here, right? So it's clear that the angles, if I just tell you what the angles are, that's not enough. If I tell you the whole matrix, that's enough, because the 2 matrices are different, but then I lose permutation invariance, because this matrix is not the same if I order the atoms in a different order. So the question is, what else do you need? So I have distances, I have angles, maybe I just go up. So maybe I have tetrahedra of points. It's a very natural step. The problem is that a postdoc of ours, Michele Ceriotti, staring at this problem for many months, invented a configuration where tetrahedra are not enough. So here's the configuration. I take this one, I copy it, and I move the top atom to the bottom. We actually created, again, a physical version of this. You can map it onto dice. And you have this pair of dice that are not equivalent, but it's shown in the paper that they share the same distances between all neighbors, so all triangles, including the center. They share all triangles of neighbors, including all tetrahedra, including the center point. It's called the bispectrum, and they're still not the same. So that's a new mathematical counterexample, and was completely shocking to any geometer, any mathematician that we've shown it to. And lots of other problems come from this. So if you use distances and triangles as descriptors, then it turns out that this non-uniqueness manifests itself as a very badly conditioned basis. If you're doing linear fitting, it introduces unwanted extra symmetries, and big problems come from modeling. This is just a little aside that if you can generate configurations that are degenerate in this sense, even when you use message passing neural networks. So iterating message passing neural networks, iterating features many times, which does create high body order terms, not just dimers, trimers, tetrahedra, is not enough. So here are, again, I won't go through the detail, but in this paper by Michele Ceriotti, there are two configurations generated, which are inequivalent, and any order of message passing makes them look the same. So let me show you what the current solution is. There is no mathematical answer at the moment of what is the minimal set of descriptors that is enough. We have partial answers, and we have a system of generating higher and higher order objects, and some of them have been shown to be enough. So let me walk back a little bit and look at this first set of descriptors called SOAP 2013. They correspond to listing all the triangles. So, but it doesn't look like that. That's just, you need to actually think quite hard to see why this is equivalent to triangles. Let me walk you through it in the context of just neighbor environment. So you have a central atom at the origin, and you have a density around this atom I, and the neighbors are called J, and around each neighbor, I put a delta function or a Gaussian of some certain width. The difference is only about regularity. But what the crucial thing then is that I sum up this density over all neighbors, and I expand this density in an angular and radial basis. So YLMs, the spherical harmonics, some radial basis, and I have basis expansion coefficients. So this rho I is a permutationally invariant object. It doesn't matter what order the neighbors are in. And then if you take the sigma goes to zero limit, so you really work with delta functions, then actually there's a closed form formula for the coefficients. It's just the summing over just the basis set evaluated at Rij, right? At the vector where the neighbor is. And it turns out, and this was the introduction of SOAP, is that if you take this coefficient C and you compute C dagger C summed over M, then you get this three-dimensional tensor called the SOAP vector. For each atom I, it has indices n, n prime, and L, and it's a permutation rotational invariant. And because you have a central atom and two neighbors, this quadratic form here, it actually corresponds to triangles with one vertex at the center. That's not obvious from this construction, but it's in the paper. And we did a lot of work with that, but it's degenerate. So the framework that allows you to generalize was introduced by Ralph Drautzen and refined by my friend Christoph Ortner, 2019. It's called the atomic cluster expansion. And it looks very similar. You start with this pair basis, YLM and radial basis. Now I've inserted Zi, Zj. Those are the atomic elements, so which atom you have. I'm also changing notation because this is the notation of the original ACE paper, so we call it phi. So essentially the where we didn't have a name for that. But then you sum over J, and Ralph called it an A, so that's the atomic basis, and it's the equivalent of our C when, because you just sum over the J. And then the equivalent of the P is called bold A, but now you don't stop at the product of two of these objects, like here with C dagger C. You can have an arbitrary number of A tensors, tensor producted with itself. And that's this new, right? So arbitrary number, and that corresponds to having triangles, tetrahedra, and all the simplices up to any number of products here. And then the sort of deep insight of Ralph was that you can, instead of summing over M to get a rotational invariant, you need to use a more complicated formula, but the formula exists, and it's in the textbook. So these are called Clebsch-Gordon coefficients. And using the tensor product of these A's, if you take the appropriate coefficient from the textbook, you get this B basis, which is a linearly complete basis for all geometry. It's complete if you don't truncate. You go all the way to nu, all L's, all M's. So that's fine, and you can compute these basis functions, and in any practical case, you can go as high as you need, and that was okay for a while, for 3 years, where we introduced MACE, which is essentially doing this but multiple times. And it's very, very close. It starts similarly. You have R and Y, and these H's start out as just delta functions, Kronecker deltas, and these C's are just 1 in the first round. I'm showing you the general formula here. The next few lines are very similar. So I sum over J. These weight matrices, this B is a linear basis, so you can do linear modeling. Here, we're not going to do linear modeling. We're going to do deep learning. So lots and lots of freedoms are inserted here. So these W's are random matrices that you can optimize, and we insert them because that's how you end up getting a much, much more flexible model. But then the geometry is the same. So we take products of A's to get a bold A, the exact same Clebsch-Gordon coefficients to get our bold B's. And we don't stop there. That would be just a little bit of flexible A's. But then we accumulate these B's into a feature H on each atom, and we go back. Okay, so we go back, and having developed these features on each atom, which is just the A spaces, basically, you then go through this entire construction once again. So now you need the Clebsch-Gordon coefficients here to get your phi's, because the H has Lm indices, and the YLM has Lm indices, and the R has L indices. So you need a generalized Clebsch-Gordon coefficient to implement the rotational equivariance. You get a new phi, you get a new A, a new bold A, and a new bold B. And that is the MACE model, essentially. And it turns out, and corresponds to message passing. So going around twice is like passing the messages to each of your neighbors. These guys here were instrumental in building message passing models for atoms a few years earlier, but they didn't do it in this equivariant way, using these tensor products. And EllIS, my student who's finishing this year, finishing his PhD in 2026, was essentially his master's project was the realization that these things should be brought together. So message passing and the atomic cluster expansion. And what I don't have on this slide, but happened in 2025, is that a couple of mathematicians have proven that this two-layer ACE, so two message passed iterations of MACE, when you truncate mu to 4, gives you a unique set of descriptors. So that mathematical problem now has a partial answer. Mu equals 4, 2 layers of message passing, and you have a set of descriptors, the second round B's, from which you can reconstruct the atomic environment up to symmetries. So now that's the end of the math part. Let me show you a few examples and then talk about foundation model. So this is an ACE model, and the system here is perovskites. So perovskites are very funny materials. They are extremely hot now for making molecular electronics, for making solar panels, for making LEDs, and they are imagine that you have these octahedra with cesium sitting in the middle, and you have these lead atoms, and they form a sort of contracted tetrahedra. The tetrahedra are a bit squeezed. They don't like to just sit straight next to each other like this. And that gives rise to all the interesting behavior. So there are temperature-driven phase transitions in how these tetrahedra like to sit. So do they just squeeze and sit tightly? Do they buckle? Do they buckle in X, Y, or Z? And so on. And these lattice constants that you see here plotted, the different colors are the different lattice constants at very high temperature. You just have an average structure. Everything moves and averages out. But as you lower the temperature, certain distortions freeze out at different temperatures. And this is an empirical model for reproducing the experiment. These are the circles. And this is displaced the ACE model, which really reproduces the experimentally observed temperatures at which these delicate phase transitions change. So to make a model like this, you need data, and you generate the data using a sort of adversarial manner. So you start with nothing, and then you run MD, and the system explodes immediately. And then you fold back, you do DFT again, you expand your database, and eventually you get a model after 16 iterations that just runs MD continuously. So that's fine. And then with that, you can make, let me skip that part and just focus on the bottom bit. You can make systems like this, which is composed of 100,000 atoms. It's a nanosecond long simulation. It is DFT accurate as much as we can verify. And now the colors indicate domains of rotating this way or this way. And then the other panel is in Y, rotating this way or this way or this way or this way. And what you're seeing here is finally, for the first time, a space-time decomposition of domains of different correlations, spatio-temporal correlations of these different oscillations. And in particular, what was not known before is that the X, Y, and Z rotations that between them are uncorrelated. So you have overlap, you have large domains, and they overlap with each other and change in time. So what really changed in 2023, at very end of 2023, is that it was the first observation of a foundation model. Up to then, every model was created like how I showed. So you start from nothing, and very slowly, painfully, you build up a large database. What was realized in 2024 is that the MACE model, for the first time, and now since then, many other models, can be trained on a set of inorganic crystals. So here is a very small sample, but imagine all inorganic materials that we've ever created or dreamed of. There's about 200,000 of them, just small crystals of any kind of element arranged in a periodic manner. 50,000 are experimentally realized, 150,000 have just been generated in a computer. But if you train on the energies and forces of those, you get a MACE model that can do basically anything. What do I mean by do? Well, it's qualitative, but it's improvable. So you get a model with which you can run MD. It doesn't explode. It gives the right kind of bonding, looks sensible, and can be used to explore. And then if you want more accuracy, you want quantitative accuracy for predictions, you can fine tune. And it's a very big paper, but amongst them, we show that for some systems, you don't actually even need fine tuning. So out of the box, I'm not going to go through the details, but aqueous systems with water behave really well and quantitatively correctly. Metal organic frameworks, which the Nobel Prize was recently given for their invention, are framework structures which can be used for catalysis, gas storage, lots of interesting applications. They work out of the box. So you can do high throughput screening. This is a hypothetical screening of 13 different frameworks, 7 different metal linkers, and you can just run nanosecond MD out of the box for them. And catalysis, heterogeneous catalysis, is one of the areas where this sort of accessible length scales and time scales are really useful. And there we do need a bit of fine tuning. So these various curves are out of the box and then fine-tuned models with very, very little data. So really what changes is that instead of active learning, complicated workflows, you can fine-tune. And in the supplementary of the paper, we show that for many, many different systems, if this is some measure of accuracy out of the box, by less than 100 new DFT configurations on each, you can get to these very, very small accuracies over here for each of those systems. And so the whole workflow changes. You don't spend a year building up a database. Okay, so maybe in the last few minutes, I want to show you where we're going next. So the limitation of the current foundation models is that there's no electrostatics and spinning. And those, for many systems, it's fine. You can get away without that. But for many, it's not good enough. Because if you want to study magnetism, magnetic fields, long-range interactions are weak, but can be critical at interfaces. If you want interaction with external fields, you need that. So we want to put electrons back in. But we want to do it in a coarse-grained manner. I don't want to know the electron density. I don't want to have wave functions or orbitals. I want to have just a couple of degrees of freedom per atom. Maybe the density and the dipole moment. So you can do that, and this is there are two ways of doing it. We want to derive how to do this from DFT. So you can have an energy that's a functional of the density. I have atom I have its element number, its position, and the restricted description of the electron. So how many electrons, what orientation is the dipole. And I have that on every atom. I want a functional that gives me a total energy. And then I can optimize that to get the lowest energy configuration. There's an equivalent formulation, which is called a fixed point iteration. I have a number of elemental, what elements I have, what position I have, and what is the local potential, just electrostatic potential. And from that, I have a mapping that maps the density. And then I solve the Poisson equation, 1 over R. From density, I go back to potential, and I iterate until it's self-consistent. So we've tried both of these. Again, in a longer talk, if I spoke faster, I would give you more details. But let me show you one example. Actually, I'm going to show you this one. So this is a very difficult test system for ML potentials that really can't do anything without explicit charges. It's the defects in silica. So silica is quartz. It's like amorphous version is the glass that you have in your windows. But the crystalline version, if you take out one of the oxygen atoms, then the two silicon atoms bond, but it's a very, very delicate system. And if you add an electron or remove an electron, you can get very different geometries. And these are the 4 different geometries that we look at. And it turns out that whether we do the energy functional method or the fixed point method really, really matters. So here's an energy RMSE of our trained model. This is a force RMSE, and these are the atomic multiples, so how well we describe the electron density. And it turns out that the energies are very hard to get with the energy functional, but the fixed point method gives you a much, much better prediction of the energy. It's not that there's nothing wrong with this method, it's just very hard to train, it turns out. And then the real breakdown happens when you try to extrapolate. And that's the whole point in ML potentials. You train it on small systems, you study big systems. So it's trained on individual vacancies. Now we put 2 of them together, and we add and we remove an electron. What happens? Do you get the localization of charge, as you should on one of these? This is the table of which of the methods that work for this system, when you get the correct answer. And the only one that works is the fixed point method with a very complex many-body mapping from the potential to the density. Every other method completely fails to generalize in this system. Okay, I'm going to skip this because I'm out of time. But what I want to finish with is that I have moved to the MPI, and this is sort of the tensor of what I'm hoping to, tensor product of what I'm hoping to do there. So it's a tensor product of methods, activities, and applications, right? So we are going to do force fields and going to push the force field technology as much as possible, but we are interested in coarse graining and maybe applying these methods to electronic structure. And there are people here, Fred and Tristan, who have worked in those fields. So I'm hoping to strengthen those links. My background is materials, but I'm actually part of the liquids initiative of the Max Planck. So we're going to do fluids because these methods really bring a lot of new capability there, and maybe possibly do biochemistry as well. And then activities is, yes, we do new science, and that is how we will be eventually judged. But I think putting out these foundation models to enable everyone to do their own science is, I think of that as a core mission. And one thing that I really couldn't do at a university, and I want to leverage the Max Planck resources, is to create community. So make this new department be the hub of ML for chemistry, ML for molecular dynamics. So thanks very much. I'm sure I've overrun by a few minutes, but let's try to have a discussion.
Michael, I think we want to.
It's not rotation in there.
Next year we have our 40-year IWR Jubilee. Michael, we might want to steal the scheme and replace a few keywords in there.
I'm not promising to steal. I'm not promising that 27 things will happen, but.
No, great talk. Many thanks. And thanks for leaving time for questions also. Tobias.
Yeah, thank you for the very interesting talk. I just wanted to ask, because you also emphasize on the point that your MACE model can be fine-tuned so easily with only few data points to more specific points. And your student EllIS said the same at the SIMPLAIX workshop. So I'm wondering, maybe you're already doing it, but why don't you just fine-tune your model to very specific domains and then train a classifier that selects which fine-tuned model to use to get a better foundation model?
Every scientist who wants to study something new is going to generate a new set of fine-tuning configuration. So the reason we don't do this is because we don't know what you want to do, right? So it's the number of models that people generate is one for each project. It's not 5 new models or 6 new models, right? If you're into the business of materials discovery, you have a new material and no one's ever seen that before. So no one has a fine-tuned model for that. So I don't think of it that you could say I have very large domains of science and I'm going to make 5 models, each applicable to one. And to some extent we are doing that, but just with 2. So organic models and material models. But I don't think those should be separate. We can't do catalysis if they're separate. The reason they're separate at the moment, and this is yet another answer to your question, is that appropriate levels of DFT are different. So for molecules, you need a higher level of DFT, a more costly approximation to the real equation. Whereas for materials, it's the diversity that you really care about, and you get away with lower levels of DFT. There isn't really, and the higher level of DFT that people use for molecules, they don't work for metals at all. So actually, catalysis is a real problem because there isn't really a function at the moment that actually works. So there'll be, one of the goddesses of the field is Emily Carter, and at any conference that I've been to, someone stands up and starts showing a talk on catalysis and an example, and if they use DFT, she will stand up and say, yeah, it's all very nice, but you know that DFT doesn't work for catalysis, right? And in some sense, she's right, notwithstanding the 30 years of enormous success that qualitative understanding of catalysis has been obtained with DFT. But I think quantitatively, it's a real big problem. That's the answer. We need new theory to combine materials and molecules. Yeah.
While people think about the next question, okay, Tristan.
That's very nice. When you do fine tuning of foundation models, do you have to worry about any sort of physics or chemistry that might break, or that like biases you might start introducing, or like how easy or how systematic just fine tuning?
This is engineering, right? And those are all the worries that one has, and it I think really depends on how. Are you fine tuning for a given system? Are you fine tuning for a class of systems? Are you willing to keep adding data, or do you want to spend a month generating data and then spend a year doing science and never having to go back? I think people generally have a good experience, but this is all empirical, right? So what you don't have to worry about is the technicalities, like changing functional, changing pseudopotential, changing reference, and that's sort of all fine. As long as you, so one of the things that we do slightly differently than most practitioners is that whenever we fit the potential energy, we fit the atomization energy. So the reference is the isolated atom, and we fit the energy difference from isolated atom to, and that's an extra, if you only care about condensed phase systems or molecules, you say, why do I care about the isolated atom? It's a much harder, it is a harder fitting task because I have all my energies here and then the isolated atom is over there. Why do I want to fit this entire thing rather than just the differences here? And the answer is because, for example, when you fine tune, that isolated atom energy changes with functional, pseudopotential, everything. And so this is the real physical dysfunction from isolated atom to condensed phase is the thing that's unchanged. So we want the many-body parametrized model to represent that physical quality, not the total energy, which can be shifted arbitrarily.
I was wondering where you stand on the data augmentation versus proper building in of symmetry debate.
In some sense, that's also an empirical debate, and I think the
maybe we should explain to the audience what this is about.
So do you I said that you need rotational symmetry. Do you? Maybe some people say, no, you don't. All you need to do is take your input structures, rotate them randomly before you train, and cross your fingers. You will get an approximately rotationally invariant model. And maybe, and the question is, why would you do that? Why would you not build in physical symmetries? Maybe it's easier to train if you don't. Maybe it's faster if you don't. So that's, I'm not really seeing that. Apart from the sort of academic interest, do I need the symmetry or not? I'm not seeing that those models would be somehow systematically faster. If you look at the cutting edge literature, it's a Wild West, right? Everyone's poo-pooing everybody else's model. Everyone's selectively picking examples where their models work. So any given sample, you will see a big variance. But over years, as people get faster compute, as people realize that you need message passing, that you need multiple many-body description in each layer, everybody gets better. And so these things, I don't see a big trend that these augmented models get somehow an advantage that just keeps growing.
You say it's an empirical matter, but I can feel where your heart is on which side.
I've had very good success with building in all the symmetries. I don't see any reason to give them up. Like I've given up other things, right? So ACE is a linear model. Would I have loved to do linear modeling the rest of my life, to do science that way? Oh, absolutely. It comes with such fantastic understanding what linear modeling can do. It's not good enough. Linear models have been absolutely left in the dust by deeply parametrized equivalent message passing models. So I had to give them up.
Yeah, sadly. Yes. More questions? I wanted to come back to Tobias' question, which has a different aspect, namely just so building a mixture of experts, not the training effort, but at runtime. Yeah, as these models grow humongous, and we might see, we might go into the billions of parameters as we do with large language models. Perhaps the model can understand that, okay, to look at this pretty boring part, I don't need to, you know, send it through all of my computation.
I think distillation is something that is being done, and people do it. Whether you want to simulate, you know, a molecular dynamics simulation is a delicate beast, right? If you switch Hamiltonian, I've done that in my previous life. Bad things happen when you switch Hamiltonian, right? So distilling for a given project or a given space to make things faster is definitely something that people do. There's another very interesting and very counterintuitive thing, is that with big data, we benefit a lot. So now molecular data sets are in the hundreds of millions. Model sizes don't go up, in contrast to LLM. So the MACE model that does the kind of thing I showed is the same size as the MACE model that will do amorphous carbon with a narrow range of pressures and temperatures. Empirical fact. Making the model bigger without extra data doesn't matter. These things are regular. I think that's to do with regularity. This model, at the moment, model flexibility is not the limitation.
That's what I would have expected, that ultimately, yeah.
Maybe, but we're in, but you know, we're in engineering world. So are we ever in that regime? Maybe, not yet.
So you showed this progression from SOAP to ACE and then to MACE. Are there still any limitations to the MACE thing, or are you basically thinking if there's something more to explore there?
So I'm absolutely sure that the current models are not the final ones. I showed that electrostatics needs to be built in, and currently the way we're doing it, it's hard to train. There's lots and lots of groups who try to do different things, right? And that's fine. That's great, actually. They escape. There are people who build force fields by tokenizing XYZ files and just putting them through transformers. I'm so glad that they're doing it and not me. Okay, so it's fine. Lots of people do these things. Ultimately, you have to go beyond measuring train and test set splits. Right? So I think that's where there's now a transition. If you come to me with any model, the greatest, fanciest ideas, and you say that you gain a factor of 50% on MACE accuracy, and just that, if you don't have anything else to show, I don't care. If you gain a factor of 10 or 3, okay, that's hard, actually. But what I really care about is downstream properties, downstream accuracy. Not on energies and forces, but MD. There are many, many models that will give you, it's a kind of overtraining, right? So overfitting. So you can get point-wise accuracies that are very good, but your model maybe is too flexible, not regularized enough, not smooth enough, and you fail. So, and there are many recent examples. So Equiformer V2, Orb V2, right? They were higher in the energy force benchmarks than other models. Nobody uses them for anything. They're unusable, piles of steaming turd as models. They're the potential energy surface of 2 atoms in Equiformer V2 is like this, as a function of distance, right? Complete and utter nonsense. So that's easy to check. And Orb V3, much better, right? People have learned. Fairchem have moved from transformers to the ESAN model, which is basically a super nonlinear neck whip, right? So they have heard, they've actually seen this themselves.
Thank you.
All right, with these happy metaphors, it's a good time to close. There will be opportunity for drinks and words with the speaker, a few words, and then the last slot is to our time slot is to our colleague from HITS before Gábor needs to find his plane. On behalf of HITS, SIMPLAIX, EllIS, IWR, Gábor, many, many thanks for coming. Great talk. Thank you.